Hi, everybody. This is the lecture on section 5.2, iterated integrals or double integrals over more general regions. So there are two types. More general types of regions in the xy plane over which we can apply iterated integration. You can take a double integral really over any shaped region. We defined it over rectangles, but just a little bit of extra effort, and you can do it over any type of region. Although it's not worth doing here. But here, this type of region, you can't always iterate. So suppose you have something like this. So say this is x equal to a, x equal to b, and this is a function y equals f of x, y equals g of x. And we're interested in this region here. All right. So we call this type of region, for lack of a better word, just type 1, or first type, or whatever. And here, a is less than or equal to x is less than or equal to b, right? So the x values are between a and b. And then the y values are between here and here. Right? X values between a and b, and then y values are between g and f. Right? So that's one type of region, right? X between a and b, and y between g and f. So the first variable is bounded by constants. The second variable is bounded by functions of the first constant. Right? So these are constants for x, and then these are these are functions for x in terms of y. But you remember when we do iterated integrals, x is considered to be a constant. So fx and gx are constant valued when x is a constant. So the other type of region is the opposite, where y is bounded by a constant and x is bounded by functions. So something like this. So this is a function x equals g of y, and this is a function x equals f of y. I have it backwards from the other one. This is x equals g of y on the left, and x equals f of y on the right, and then y is between a and b. So the y is bounded by a constant, and the x is bounded by functions of y. So we call this region type 2, well, first type, second type, I mean, whatever. Silly terminology. So this is a less than or equal to y less than or equal to b. And this is g of y less than or equal to x less than or equal to f of y. Which one goes on top? Remember, x values get bigger as you go to the right. So this is right on the top, right on the right, left on the left of the x. So the left is the smaller function, the right is the larger function. All right, that's the larger function on the right, smaller function on the left. All right, because x increases as you go to the right. All right, with y, we're more sort of intuitive about it. The one on the top is bigger than the one on the bottom. All right, so some regions, so we can apply iterated integration over these types of regions because when you integrate with respect to this variable x first, y is considered to be a constant. So these are constant bounds. And then the x's go away, and these are constant bounds. Here, you integrate with respect to y first, and these are constant bounds. And then the y's go away, and these are constant bounds for x. So you can apply iterated integration to these types of regions. So for example, not all regions can be described in both ways. As both type 1 and type 2 but some can be. So let's take a look at this region here. So this is the function y equals x squared from 0, 0 to 1, 1. So this is x equal to 1, y equal to 1, and then we're looking at this region here. Okay, and that's 0, 0 right there, of course. I didn't label it. This is the function y equals x squared. So you can describe that as a type 1 or type 2 or whichever type. I mean, here x is between 0 and 1. 0 less than or equal to x less than or equal to 1, and then y is between x squared and 0. All right, here's x squared, and here's 0. So 0 less than or equal to y less than or equal to x squared. So that's one description. And then for the other variable, the other way around, first the y, again, is between 0 and 1. 0 is less than or equal to y, less than or equal to 1. And then the y value, so this is the function y equals x squared. All right? So this is y equals x squared, but it's also x equal to square root of y. Right, so the y value, or sorry, the x value, y is between 0 and 1, and then the x value is between this function on the left, which is square root of y, and this function on the right, which is y equal to 1. Right? Square root of y to 1. Square root of y is less than or equal to x, less than or equal to 1. Right? So that's a description as both types. X is bounded by constants, y bounded by functions of x, which can be held constant, y bounded by constants, and then x bounded by functions of y, which are held constant. So now you can do the same iterated integration process over these types of regions as we did in the previous section. Okay, but the ordering is forced. So let's take now we can apply iteration to calculate double integrals double integral over r f x y dA, where r is type 1 or type 2. Okay, so for example, not for example, but when a is less than or equal to x is less than or equal to b, and g of x is less than or equal to, so if this is r, g of x is less than or equal to y is less than or equal to f of x. In this case, the double integral over r f x y dA is equal to the iterated integral. So you can only do it one way here, from g of x to f of x, and then from a to b, f x y. So first we're doing integration with regard to y, and then integration with regard to x. So when you're doing integration with regard to y here on the inside, x is held constant. So these fx and gx are constants. And you're doing the antiderivative with respect to y, where x is a constant. And then after doing that, you'd be left with a function in terms of x, and then you do the integral as usual. And then if r is the other type, type 2, then a is less than or equal to y is less than or equal to b, and g of y is less than or equal to x is less than or equal to f of y. In this case, the double integral over the region R can be calculated as follows, using this iterated integral, dx dy. So these are f of y, g of y. Okay? Now, what's interesting is when a region can be described in both ways, as both type 1 and type 2, okay, then the integral can be calculated both ways. The double integral can be calculated in two ways. Different ways with the answer guaranteed to be the same each time. Which is like what we were doing said in the last section with integration over rectangles, double integration over rectangles. But here it's got more interest. Here, like, you can have two ways to calculate it, but maybe one way is a lot easier than the other way, or maybe one way is not even possible. So let's take an example to show that. So let's go back to this region here. So let's calculate the double integral over this region R, so this is R, of x cosine y dA, right, in two different ways. Right, as a type 1 and type 2 region. Okay? Well, the first type, the double integral over R of x cosine of y dA is equal to, so we'll use this type here. X goes from 0 to 1, and y goes from 0 to x squared. 0 to x squared for y, 0 to 1 for x, x cosine y dy dx. So the antiderivative with regard to y. Okay, x is a constant. Antiderivative with regard to y is just sine y. X sine y. And then you're going to evaluate from y equals 0 to y equals x squared. Right? So evaluating at x squared, we get x sine x squared. And evaluating at 0, we get x sine of 0. Sine of 0 is 0. Right? So let's just leave that out. So we have x sine x squared, integral from 0 to 1. Right? All the y's are gone, and now we just have a function with regard to x, an ordinary single variable integral. This one we can do with a u substitution. You let u equal x squared. So du dx is equal to 2x. So du over 2x is dx. So this becomes the integral from 0 x equals 0 to x equals 1 x sine u du over minus 2x. This x cancels. So this is minus 1/2 the integral from x equals 0 to x equals 1 sine u du. So antiderivative is 1/2 cosine u. Negative goes away. 1/2 cosine u from x equals 0 to x equals 1. So this is 1/2 cosine x squared from x equals 0 to 1. So we get 1/2 cosine of 1 minus 1/2 cosine of 0. Cosine of 0 is 1. So this is cosine of 1 minus 1 over 2. Wait a minute. Oh, there's no minus sign there. What did I do? Minus 2x. It's just 2x. No minus sign. 1/2, 1/2. So now there's a minus sign because we did the antiderivative. So this is minus plus. So it's 1 minus cosine of 1 over 2. So there's the final answer. 1 minus cosine of 1 over 2. Now, let's calculate the second way. Okay, so here the region is described in this way. Right? First we described it this way, right? So actually let me put that there. Alright, so we use this description here. Now we're going to use this description. So, this is R. This is the region R. So the integral, double integral, over R of x cosine y dA is equal to the double integral. So square root of y to 1, 0 to 1, x cosine y dx dy. So we're integrating with regard to x first, where y is a constant. So this is the integral from 0 to 1. Cosine of y is constant, so the antiderivative with regard to x is 1/2 x squared cosine of y from x equals root y to x equals 1 dy. Right? And this is equal to what? Evaluating at 1, we get 1/2 cosine y. And then evaluating at square root y, we get 1/2. Let me go down a line. Minus 1/2 y cosine y dy. So now all the x's are gone and everything is in terms of y. So let's split this integral into two integrals. Integral from 0 to 1, 1/2 y, cosine y dy, minus the integral from 0 to 1, 1/2 y cosine y dy. Well, the first integral, the antiderivative is just 1/2 sine of y from 0 to 1. Right. 1/2 sine of y. Let's calculate this one first and then the other one second. Minus 1/2 the integral from 0 to 1 y cosine y. So this is sine of 1/2 sine of 1 minus 0 minus the integral from 0 to 1 y cosine y dy. So this one you need to use integration by parts. Right, so we let u equal the polynomial y and dv equal cosine y dy. So now du is just dy, and v is antiderivative of cosine y, which is sine of y. So this whole expression is equal to 1/2 sine of 1 minus 1/2 u times v, y sine y, evaluated from y equals 0 to y equals 1, minus the integral v du sine of y dy, and that's from 0 to 1. So this is equal to 1/2 sine of 1 minus 1/2 parentheses. So this is 1 sine 1, it's just sine 1, minus sine 0, which is 0, minus antiderivative of sine y is minus cosine of y from 0 to 1. Right? So we get 1/2 sine of 1 minus 1/2 sine of 1 plus cosine of 1 minus cosine of 0, which is just 1. So this and this cancel, and we're left with negative, right, of this. So that's equal to 1 minus cosine of 1 over 2. Same answer as before. All right, 1 minus cosine 1 over 2, 1 minus cosine 1 over 2. Now, both ways were a little on the tricky side. This one just required a u substitution. This one required a, integration by parts. Right? I mean, depending on which one you like better, or you hate either one, or whatever the case might be. But I think the first one was easier. Now, sometimes you can't even do the integral in one way. Sometimes you have to do it in, as type 1 or type 2. Okay, let's try another example. Calculate the volume of the following tetrahedron. A tetrahedron is a four-sided figure in which each side is a triangle. So here we'll say that this is 3, 2, 1, and I'm going to have this plane here as one side of the tetrahedron. All right, and the other sides of the tetrahedron are the triangle in the xy plane, the triangle in the yz plane, and the triangle in the xz plane. Okay? So, well, what's this plane? This is the plane, right? So it's got z-intercept, z equal to 3, x-intercept, x equal to 1, y-intercept, y equal to 2. So you can just write it like this: x over 1 plus y over 2 plus z over 3 equals 1. Right? So if you write it like this in a standard form, then if you solve for z, it becomes z is equal to 3 minus 3x minus 3 halves y. All right, now if you want to calculate the volume of a solid in xyz space, okay, in this instance we can describe the solid as the region between the triangle and the xy plane. So here's x, well, let's draw it three-dimensionally. X equal to 1, y equal to 2, like that. Between that triangle and the xy plane and the plane z is equal to 3 minus 3x minus 3 halves y. So it's the double integral is just the, so we'll call this triangle T, the double integral over T of 1 dA. So if you just want the volume of a solid, rather than calculating, or sorry, not 1, is just 3 minus 3x minus 3 halves y dA. Okay? So now what's that triangle? Let's take a look at that triangle. So this is x equal to 1, y equal to 2, and this is the line. What's this line? So we can do this as type 1 or type 2. There's no real reason to do it both ways here. But this is the line. Y is equal to, and what's the slope here? Minus 2, minus 2x plus 2. That's 2 minus 2x. So this is 0 less than or equal to x, less than or equal to 1, 0 less than or equal to y, less than or equal to 2 minus 2x. Right, so that is a type 1 region. So the volume of that tetrahedron is the double integral over the triangle T, 3 minus 3x minus 3 halves y dA, which is equal to the iterated integral from 0 to 2 minus 2x and 0 to 1, 3 minus 3x minus 3 halves y, and then you're using boundaries for in terms of x, so we want to hold x as a constant, so we do y first. So dy dx. So it's the reverse order of this. All right, so the antiderivative with regard to y. So 3 minus 3x, it's got no y's in it. So that's all just a constant, y. Minus 3/4 y squared. From y equals 0 to y equals 2 minus 2x dx. So this is equal to, now before I evaluate, I want to do a little bit of algebra to try to simplify things. Let's factor out a y. And we get 3 minus 3x minus 3/4 y. From y equals 0 to y equals 2 minus 2x dx. So evaluating at 2 minus 2x, we have 2 minus 2x, 3 minus 3x, minus 3/4 2 minus 2x dx. So now let's simplify, and then evaluating at 0, you get 0, of course. All right, so we evaluate at 2 minus 2x, we get that. And then evaluating at 0, we get 0. So we try to simplify the calculations as much as possible and not write, unnecessary things. Minus 0 times 1, that kind of thing. So this is equal to the integral from 0 to 1, 2 minus 2x. Let's see what we have here. So we have 3 minus 3 halves. So that gives you 3 halves. Right? 3 minus 3 halves. Minus 3x minus 3 halves x. So that's 3 halves x. I guess we multiply by 2 and you get 3 halves. So 3 halves minus 3 halves x dx. So integral from 0 to 1, factor out 2, factor out 3 halves, and we're just left with 3 times 1 minus x, 1 minus x. Right, so that's the integral 3 times the integral from 0 to 1, 1 minus x squared dx. Antiderivative minus 3 over 3, so it's minus 1 minus x to the third. So that was using a u substitution, but I just did it as quickly as I could. From 0 to 1, so evaluating at 1, you get 0, and then evaluating at 0, you get 1. So it's 0 minus 1, so it's 1. Okay, So the volume of that thing is 1. Anyway, we can check that answer. It's well known, although maybe you don't know it, but it is well known that the volume of a three-dimensional cone so if you have a two-dimensional region here, R, and then you have this point anywhere, sort of, doesn't have to be directly above, can be just anywhere like above the XY plane. So you've got this region R in the XY plane. And then you've got this point up here, and its perpendicular height is H. The volume of this thing is equal to H over 3 times the area of R. It's just 1/3 the height of the area of the base. So that's the height of any cone construction. So that's what a cone is. You get this region in the XY plane, and then this point that you're just sort of stretching up the region to. And the volume of this thing is always just the height over 3 times the area of R. In our case, so the area of the base is equal to, well, it's 1/2 1 times 2, which is 1. And then the height is 3. Right? So H over 3 times the area of the base is 1. Right? So that's a nice check on that calculation there. Okay, so that's the end of the lecture on this section.